Well, greetings, everybody. So here I have a problem from our assignment, and it deals with the trapezoidal rule and Simpson's rule. And it goes like this. We'll calculate the trapezoidal and Simpson's rule estimates, and then talk about what the error involved in those estimates is going to be. All estimates involve some kind of error, otherwise they wouldn't be estimates. Okay. Before I get into this, one thing that I won't explain in this video is the nature of the partitions, okay? Because the trapezoidal rule and Simpson's rule both involve partitions, and then we do our calculations based on those partitions. If you want to learn a little bit about that aspect of the rules, then you can look at this introductory video I have here about the trapezoidal rule. Okay, so let's get started on it. So we have this integral, the integral from 0 to pi 3 sine t dt, that we're trying to estimate with the trapezoidal rule. Let's start there. And it says we'll use n is equal to 4, and you could think of that as 4 trapezoids. Like if I was to inscribe within this integral on a graph 4 trapezoids to cover the area under the curve. That's what that means. Or sometimes we say that the partition has 4 subintervals. Okay. Now, the partition in this case is going to be 0, pi over 4, pi over 2, 3 pi over 4, and pi. What we do is we calculate the trapezoid width, or the subinterval width. That's going to be the upper bound of integration minus the lower bound of integration, pi minus 0 in our case, divide by the number of trapezoids that you have, which is 4 in this case. Okay, so the width of each gap in the partition, I guess you could say, is pi over 4. Now, to get the partition, we'll count from 0 to pi, beginning to end by pi over 4. 0, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So there's your partition. Now, in that introductory video that I mentioned, this formula will be there. Okay, that's the trapezoidal estimate from n trapezoids. Okay, so this is what you'll see if you complete that with our partition. All right, so in any case, from there I get this b minus a, upper bound of integration minus lower bound of integration, pi minus 0 over 2 times the number of trapezoids, which is 4 in our case. And then notice here that each element of the partition goes into our function like so. Okay, so our function in our integral is 3 sine t. I accidentally wrote x here, but it doesn't matter. So, and into that function I put these elements of the partition. And so, for example, this one right here, f of 3 pi over 4 is 3 sine 3 pi over 4. Okay, now to do this part, like at this point I've got to do this calculation. It's tedious, but I can use a scientific calculator, a real simple one like this. I can do that with a calculator like this. It's a little bit tedious, but I can do it. It's a little bit easier if I use a graphing calculator with a little bit nicer interface, but nonetheless, even with a basic scientific calculator, this can be done. Okay, now I'll break down the calculations for you a little bit. I get this here, and I get my final answer for the trapezoidal estimate with 4 trapezoids being 5.6883. So that's this number that you see here. It's rounded to 4 decimal places on my math lab. Okay, so that's how you get started, is to calculate the trapezoidal estimate with 4 trapezoids in this case. Now, from here, as I was saying from the beginning, the trapezoidal rule is just an estimate. It doesn't tell us exactly what the answer to this integral is going to be, or at least we shouldn't expect it to. And so all estimates contain error, and I want to tell you what the error is. Okay, so wouldn't it make sense that I could calculate the error in my estimate by taking the actual answer to that integral and subtracting it from my trapezoidal estimate? I mean, this is like the perfect true answer, that this integral, whatever the answer that is, and then this is the estimate. So if you subtract them and take the absolute value, that's the error. Okay, you just find their difference. So this integral here, could you tell me its perfect and true answer? Well, for this integral you could. The way you calculate this integral is you find the antiderivative of 3 sine t, which is negative 3 cosine t, and evaluate it between the bounds 0 to pi, and you get 6, okay? So the perfect true answer to that integral is 6, and our estimate by the trapezoidal rule is like 5.6. See, they're different, okay? And then I told you that would happen. This is only an estimate. So if I subtract those numbers, I will calculate and take the absolute value, I'll get the error in my estimate, and that turns out to be 0.3116 or so. In my math lab, it's rounded right here to 4 decimal places. Okay, that's my error, ET. So now, if we're working with estimates, such as by using the trapezoidal rule, I not only in this case can I tell you what the error is, because I have my estimate and I have the perfect and true answer. I subtract them, I can tell you how wrong I am. That's how wrong I am right there by using the trapezoidal rule. But could you predict the error? Because you might think like, well, the idea is I don't know the answer to this integral, so can I predict something about how wrong I'm going to be? So you can. We can use this formula. This is the upper bound on the error when using the trapezoidal rule. It's based on 3 things, really. Capital M, which is the maximum value of the absolute value of the second derivative of the function in the integral, okay, on the interval that's given. The second thing is the bounds of integration, b subtract a to the 3rd power. B and a are the bounds of integration in the integral that you're working with. And then n, the number of trapezoids, or the number of subintervals in your partition. Okay? All right, so it just depends on those 3 things. Now, the only thing that is difficult about this to calculate might be m, the maximum value of the absolute value of the second derivative on the interval. B minus a, well, that's just the bounds of integration subtracted, and n's the number of trapezoids. So those you should be given in the beginning, okay? All right, so let's talk about this. How can we calculate m based on the second derivative of our function? Okay, all right. So the function in the integral is 3 sine t, right? The second derivative I work up to is negative 3 sine t. And I want to look at that on the interval 0 to pi. So here I've drawn this sine wave, negative 3 sine t. And here I'm looking at it from 0 to pi. Now, m could be difficult to find. You might have to find a maximum or minimum value of a function on an interval. But in the case of the problems I put on the assignment, it shouldn't be that difficult. Like, this is a sine wave, okay? And it has an amplitude of 3. So like this minimum value down here is 3, okay, at that point down there, negative 3, sorry. And then this is 3. Okay, so this sine wave is going to oscillate between negative 3 and 3 and negative 3 and 3 forever. Looking at just the interval from 0 to pi, then the minimum, the lowest, the furthest down it gets is negative 3, but I'm thinking about the absolute value. I'm trying to find, if all these points were positive, what's the biggest that the y coordinate would be? And so in this case, it'll be 3, okay? So the maximum value of the second derivative's absolute value on this interval here, 0 to pi, is going to be 3, because that minimum value is negative 3. So let's complete this formula here, which gives us an upper bound on the error. It allows us to predict something about how wrong we're going to be if we use the trapezoidal rule. So it'll be m, the largest value of the absolute value of the second derivative on the interval, that's 3. B minus a, upper bound of integration minus lower bound of integration, pi minus 0, 3rd power, divided by 12 n, the number of trapezoids, 4 in this case squared. And I calculate that and it says 0.48447, okay? So that is this part right here, okay? An upper bound for the error in the trapezoidal rule, 0.4845. What did I get down here? 0.48447. Yeah, so that would still round to 4 decimal places to 0.4845. So all that I would say is like, well, if I use the trapezoidal rule, I know I'm going to be wrong, but this is the most I'm going to be wrong. Okay, it's an upper bound. It's not telling me what the error will be, but it will tell me this is the most you can be wrong. That's what we mean by upper bound. Okay, all right. Now let's give a summary of that, because there were lots of things working together here. Okay, I wanted to estimate the answer to this integral by the trapezoidal rule with 4 trapezoids or 4 subintervals. The actual answer to that integral was 6. And if I use the trapezoidal rule, I got 5.6. So the trapezoidal rule is wrong, but I can tell you how wrong by calculating the error, and that's our estimate minus the actual answer. It's that number. And then on top of that, if I needed to, I could predict something about the error, because we need to manage the error somehow. If we're going to be working with estimates, there's going to be error. We'll be wrong to some degree. It'd be nice to know something about that. So I can predict an upper bound based on that. One more thing you might say is, if you know the answer to this integral, if you know its perfect and true answer is 6, then why are you bothering with an estimate? Well, the answer to that is this is an exercise. So this question allows you to go through all the aspects of using the trapezoidal rule as an estimate. It might be, real quick, that we see a question like this where we don't have the function we're working with. In this case, we don't know this function. We just have a bunch of measurements. Like I have some isolated points on its graph, but I don't know the entire function. I don't have a formula for it. So in that case, like I don't have an option of telling you what this integral is exactly, because h of x is unknown there. I just have these data points, these measurements. Okay, so there, like calculating that integral directly is just not an option. I can predict something about how wrong I would be with the trapezoidal rule, because I might know that the error depends on m, which is basically telling us something about the curvature of the graph. The more it's curved, the more the error is going to be magnified. Bounds of integration, the further they are apart, the more the error is going to be magnified. And the number of trapezoids or subintervals, the more of those there are, the less the error is going to be magnified. So I could, even if in that case, if I couldn't predict the error, I can tell you its limitations. All right, so that's the trapezoidal rule. Now the second part was calculating the same sorts of things for Simpson's rule. Okay, use 4 subintervals, 4 steps, find an upper bound for the error, find the actual error, and compare with the actual value of the integral. Nothing would change in that. The concept is the same. The way that you would think through it is the same. But it's just that some of the formulas are a little bit different. Okay, so with Simpson's rule, with the Simpson's rule aspect of this question, then the partition is going to be found the exact same way. So the partition is no different in this case. But the Simpson's rule estimate is according to this formula, which even looks like a lot like the trapezoidal formula. Okay, but it is different. There it is. And in our case, that's going to play out like this. Okay, and then there's my Simpson's rule estimate with 4 subintervals. All right. Now, that's one thing that's different about it. This formula, slightly different. The other thing is this formula that calculates an upper bound on the error. So the Simpson's rule still gives us an estimate. There's still going to be error. We're still going to be wrong. And we can still predict something about the error by calculating its upper bound. Even this looks a lot like the trapezoidal formula. It still depends on this number m, slightly different in this case, the bounds of integration, and the number of subintervals. Okay, the difference is you see the exponents, some of the other numbers are different, and m this time is the maximum value of the 4th derivative's absolute value on the interval. So I think if you could calculate this for the trapezoidal, you could calculate this for Simpson's. M would be the same as it was over here. Why is that? Well, if I were to calculate these derivatives, I'm just going to be alternating between sines and cosines and so on this interval. And it's a simple curve with the same sorts of oscillations. I can find that maximum value the same way. I don't see that there's any complicated analysis to find this part of this problem, because sine and cosine waves are basic functions that we should know enough about already to do that. Okay? All right, so that part's a little bit different in Simpson's rule. This part's a little bit different. But still, I think if you have these formulas and if you understand and can do the calculations for the trapezoidal rule, then Simpson's rule shouldn't be a problem either.